A data scientist is more of a general purpose machine learning uh, job. So you would be tasked to do a lot of different things within machine learning, within data science. This could include, database administration. This could include data engineering, a wide variety of things, and it's kind of a catch-all. And a lot of companies use this, especially when they're starting up their data science programs and organizations, because it's a very general purpose. Once you have companies that are more focused on specific data objectives, you'll start to see the ones below as more very specific roles. So for machine learning engineer, this is what I currently am, is very much focused on the machine learning infrastructure. So if you think about, for example, I like to use Facebook as an example just because it's something everyone knows. But if I'm trying to predict whether or not people will click on a specific ad, there's a lot of infrastructure that has to go under the scenes to make that work. So a lot of that is, how do I design my models correctly? How do I make sure that my compute is appropriate for what I'm trying to do? How do I know that my results are correct? All of that kind of falls under this ML infrastructure. But then a couple of the other ones could be a big data engineer. So what if I'm working with petabytes of data? How do I do that effectively and at scale? It's actually a very challenging problem, and something that, with a lot of the domains that industrial engineering goes across, that it really is a really good opportunity for that. Cloud architects. So this is, how do we do machine learning in the cloud? Research scientists. So this is ML R&D. This is kind of what I was talking about with like Google's DeepMind or Facebook's FAIR. This is kind of the in-between between academia and industry, where it's a lot of research and development, and a little bit less focused on developing a specific product. And then there's a data analyst, which is more reporting and visualization. This would be one I would say is definitely below what an IE PhD would do, but wanted to put it on here as kind of, this is another thing that exists. On the right, I have just an example of kind of what the ranks would be, and these are very much company dependent, but this is just kind of an idea. So at the lowest level, you would have kind of a junior data scientist, then a normal data scientist, a senior, principal, a director, a senior director, a vice president, and then all the way up to like a chief data officer, depending on the company. That's more just to kind of give you an idea of what that kind of looks like. But with that, so kind of thinking about data science and industry, if you wanted to move into that field, what would be the most important skill? And the only one that I will ensure that I ask in every interview to make sure that they are good at this in a data science role is communication. It's one that is not technical, in the sense that it's not something you can necessarily, it's not an algorithmic perspective, but communication, especially in industry, is an incredibly important skill. And the reason for this is that data science, and think about optimization, or machine learning, it's deeply technical, right? We're doing things that are very heavy math, things that are very complicated, but you will be working with lots of non-technical people, and a lot of those non-technical people are going to be the ones making business decisions. If you think about the CEO of a big company, something like Apple or something, the CEO of Apple does not understand data science extremely well, as any of us here would. But they have to make decisions based on what the people who do understand data science tell them. So really, a very important part of being a data scientist is communicating well, and you need to be able to communicate why your work is important. And I put broader impacts in parentheses here, because this was one thing for my PhD. Dr. Bian always stressed from NSF, they had the intellectual merit and the broader impacts, and you always had to have both in your paper. Otherwise, it was not going to be received well. And I realize now how important that is, because it truly is explaining why your work is important, and explaining how, more so why it's important rather than how you did it, is extremely important. And I wanted to give a quick example of that. So let's say that you're working as a data scientist. You have a machine learning model that you've been working on for a while, and you just found out a new way to increase your accuracy. So if you were talking to a fellow data scientist, so someone who does have the same technical background as you may give them the first answer, which is, I used sklearn, grid search CV to optimize our hyperparameters and increase our accuracy from 97 to 97.8% on a held out test set. This is a very technical description. This is how you did it, right? This is a very much, I need you to know and make sure that I did this correctly. Now, if you, let's say we take a step back and let's say we're reporting the same thing to our team lead, you may say, well, I was able to improve the accuracy of our model through hyperparameter optimization. I validated my results, and this improvement is going to lead to an expected $50,000 in additional gain over what was previously expected. So to the team lead level, you're still getting a little bit into the technical part, but now it's a little bit more on, well, what does this actually mean? Like, why is this important? And then if you were going to take it even a step back and go to the director of data science or to your direct customer, you may say something like, I improved the model for our new ad campaign. This improvement should gain our company $50,000 over what was initially expected. At the director level, they don't really care how you did it. They don't want all of the nitty gritty technical details. They want the broader impacts. So this is a good way to think of it using kind of the NSF structure earlier, is you have to be able to talk across all three of these spectrums. It's something that's difficult, and it takes a lot of work, and it's something that I continue to work on, and I know all of you will as well. There's in academia, a lot of the time we're stuck at the top one. We're stuck at intellectual merit. We want to tell you about how we did this thing, why, and how it's the best thing ever. This algorithm improves this performance on 10%. But really, when you get into an industry environment, it's much more important to explain why that's important. I see, yes, you got this algorithm to be 10% better, but what does that actually do for me? And that's a very, very important thing. This is, like I said, this is the only question of all the interviews I've done at this point, about 20 interviews or so for various data scientists. And I always will ask them I will always ask them a question to understand how well they can communicate across these three spectrums. Because if you can't do this, it's much, much more difficult for you to get buy-in from your work. And obviously, at the end of the day, we all want our work to be valued and for other people to see it as impressive as we do. And so this is something that you have to do. And I would argue, honestly, this is something even for academia that you need to do. But it, in my opinion, becomes very important on the industry side. So one thing I wanted to quickly show, here's an example of what I would say is good communication. So if you think about Apple at their keynotes, they're giving you the very high level version. So things like, we have cinematic mode, we have this new center shift wide camera, we have longer battery life. They're not telling you how they did all of that. They're telling you what's the important stuff that you as a consumer care about. But you can imagine, for example, on the longer battery life, there were hardware and software engineers who worked, hours, weeks, months to improve that, to get, how can we get longer battery life? It was a very technical thing, going down to the watts, to how all of these parts interact with each other. But ultimately, on what they showed to the consumer, to us, they just said longer battery life. And we all know what that means. And that's the level that we need to understand it at. And so this is one thing I always try and think of, is whenever I'm giving a presentation on something that is very technical, and oftentimes with data science, it is very technical, is how can you explain it to someone who has no data science background at all? So I know I harped on that a lot. The reason I do that is because of how important it is. And one of the nice benefits is, to me, this was one of the major benefits of getting a PhD, is learning how to communicate well, because getting a PhD really forces you to learn how to communicate well. If you think about even just the act of writing a paper. So I have, my new algorithm that I've found that is super awesome. Well, that's the methods section. That's generally section 3. But now I need to do the introduction. I need to explain, why is this important? Why should you care about it? I need to do the literature review. So that's kind of writing a logical argument, using references to support my argument. And then after I've explained my method, I need to prove to you that it works. So do some set of validation. And then I'm going to tell you again why it's important technically, and then how is this going to be used more broadly in the world. And so really, that's one of to me, the biggest benefits of doing a PhD is it really forces you to learn how to communicate well, because it's not something at the undergrad level that you really get. You at the undergrad level, a lot of times you're just doing homework, submitting homework, taking tests, seeing how well you do on the test. But you're not really having to communicate what you learn to a wide audience. But in your PhD, you really do. And this continues with, presenting your work to others at conferences, working with your lab mates, working with your advisor, which can be very similar to your relationship with a team lead in an organization, and also working inside of an organization. So if you think about, I need my card is not working, I need a new computer. So really trying to better yourself on this communication so that you understand what all resources are available to you and maximizing what you can through that communication. Alongside that, kind of moving into a little bit more of the, what you say, soft versus hard skills, is you definitely will get the intellectual merit part. You will be, when you finish your PhD, you will be a world-renowned expert in your dissertation topic. You will know more than anyone else in the entire world on your specific topic. And along the way, you will get very good at coding, and you will understand mathematical frameworks very well. So when I was doing my PhD at Mississippi State, I generally did almost everything in Python. Luckily enough, that's a very strongly desired language for data science in general. R, MATLAB are also common, but Python and C++ are the ones that I've come across that are the most desired. But really learning how to code well, being able to do that. The languages, you can always learn a new language, but that's something that I learned very well throughout my PhD that has paid huge dividends for all of my work post-PhD. The other main thing is kind of the mathematical frameworks, the theoretical understanding. Taking classes on the heuristics of optimization, fundamentals of machine learning, learning about machine learning on the computing side. You're going to learn a lot of the theoretical knowledge that you need to be able to apply these techniques to new and novel problems. So you will not have any, you should not have any deficiency in kind of your intellectual merit of what coming out of your PhD. The other main benefit an ISE PhD will get you is a lot of domain-specific expertise. And this will depend a bit on your advisor, what area they're in, and what area your dissertation kind of focuses on. So supply chain is a huge area for data science. There's so many openings in a variety of supply chain organizations. And this, logistics, queuing, there are so many things that you will learn within industrial engineering that directly apply to the supply chain world. Manufacturing is another big one. That's what I did most of my PhD in, is applying machine learning in manufacturing. And there's a lot of great opportunities as well there. And then athlete engineering, which is something that was kind of starting up while I was still a PhD, but I know has grown a lot recently in the industrial engineering department. You look at most pro sports teams, they all have data science teams trying to predict, how can we make our athletes slightly better? How can we better draft players? So depending on what your expertise that you gain during your PhD, you can definitely leverage that into moving into a job that uses that, and you will be looked at, having that expertise to make an impact much sooner. So with that, now I'm going to jump into the differences of what did I not really learn in my PhD, but I've learned in industry since then. And I brought this slide back because I think it's important to quickly touch on this, is that the reason why I didn't learn a lot of what I'm going to talk about in the next few slides in my PhD is because of the differences in objectives between academia and industry. In academia, we have small groups focusing on intellectual merit. We're not doing large-scale product development. But in industry, we have large groups of people working on the same thing. We have product development. We're really focusing a lot more on the broader impacts. How do we make sure that our customer likes what we're doing? And because of that, there are a lot of initial problems that crop up that have solutions through various tools. So I've put together a list of them, and I'm kind of going to introduce each one with the problem that initially arises, and then talk a little bit about the tool after that. So here are the 6 main things that I would say that I use pretty consistently now in my job that I really didn't learn at MSU. And again, like the note at the bottom says, these are all things that are needed in kind of enterprise scale companies. When you start scaling it and you have 10, 20, 30 people working on the same project, there's a lot of additional things that you need to make sure that you're doing that correctly, you're doing that well. But when you're in a small research group, a lot of this is just kind of unnecessary overhead. So I don't want you to get the impression that I didn't learn these at MSU because they aren't, that MSU failed in any way. That's not what I'm trying to say. What I'm trying to say is that these are solving a problem that doesn't really exist in small research group. But if you're interested in moving into an industry data science position, knowing these things alongside of a PhD makes you a much more valuable candidate for future jobs, because that's less that you need to learn kind of starting on day one. So I'll go through these one by one. We'll start with SQL. So SQL, the problem that it's trying to solve is your company has massive databases full of past transactional data, and you need to query for specific data. Imagine you're working in a supply chain company where you have hundreds of millions of past transactions, and you need to find a trend in a specific product type to identify how much we should be stocking the shelves with that product type so that our customers don't run out when they're buying it in the store. Generally, I mean, you're thinking about looking at a big database, and really when you thinking about databases and relational data, the solution almost always is SQL. Well, I know when during my PhD, we did a lot of data analysis, but a lot of the data that we did, we ultimately used CSVs and some versioning. We didn't move it into a full database because there's a lot of overhead there. You gain a lot of really nice things by putting it into a full database. But again, this is the difference between academia and industry. Sometimes that overhead's not worth it for smaller research groups. SQL is the industry standard for querying relational databases. And what I mean by relational databases is I have a consistent schema, meaning it has the same columns, and I'm just adding data to that table and wanting to query from it. It has its own language. It's very straightforward to learn. And for many data scientist positions, SQL is a requirement. It is not a nice to have. So this is something, and I have a slide later talking about kind of my recommendations. This is definitely one I would strongly urge for you to learn if you're interested in kind of an industry position within data science. The next one is Git and GitHub. The problem that it is trying to solve is you and a team member are working on the same code. How do you make sure that both of your changes to the code are incorporated? So I know probably all of us, as we were going through school, we always had things like, this is my paper version 1, this is my paper version 2, this is my paper version 3, this is my paper final version. I really promise I'm not changing this anymore. And you continue to just add versions and versions and versions, and it obviously messes up your folder structure, and you just have a lot of copies of the same document. The solution to get around this is called Git. It is a version control for code. You can technically use it for any sort of documentation or files, but most often used for code. It allows multiple developers to work on the same code at the same time without breaking everyone's code. Seem like overhead at first, especially for projects where you're working by yourself, but starting to get habits in grad school is incredibly important. And I've added a cheat sheet here, and then there's also kind of at the end of the presentation, there are some references on where to learn Git. Git is extremely important, and no matter what data science position you go into, I can guarantee you that you will be using Git in some capacity. It makes code control so much nicer. And again, it's a thing where once you have a lot of developers, you need something like this so that you know what's the latest version of my code, what am I pushing out as my final product, what am I going to send if I'm facebook.com, what is the version of the code that I'm sending out so that when people go to facebook.com, that's the version that they're seeing. Now, Git is strongly tied to GitHub, and basically GitHub is just a remote repository to store your code. So when you do Git, you can do it locally. So you can have it to where you just save your files on your computer, but it's most common to use a local and a remote repository. The most common ones being GitHub, Bitbucket, GitLab, and AWS Code Commit. and other cloud computing sources. If you want to have a GUI or a graphical user interface, I recommend GitKraken or GitHub Desktop. They're both great tools to help you with Git and GitHub, but you can also use the command line using what's called Git Bash. I don't want to go into too much detail about how to do this. I more want to give this as kind of an overview, but happy to answer questions later on if you have specific questions about Git. The next thing, very important, is code testing. So, let's say I just added code to my company's project. How do I know that it works as intended? Well, the way that you do this is code testing. And this is available in almost every coding language, but it's something that in academia, a lot of times we're doing, manual testing. We're doing things where we're writing scripts one time, or maybe, one or two times for a project, and then we go to a new project, and a lot of times we end up having to rewrite a lot of the same code. In industry, what you end up having a lot of times is you have code that's written at one point, and then you continue to reuse that code because you have a lot of things that end up being very similar. Whereas in research, a lot of times there's not a ton of replicating work across different projects. It definitely depends on the project, but where code testing comes in is I'm using that, replicating across other projects. I need to make sure that it always works as I intend. And so what I will end up doing is I will take my code. I will do tests on the code. So for example, testing inputs and outputs, testing that the types are correct. And a lot of this is to ensure that your code is functional, and that it's not going to break something else. So you can imagine if, let's say, Facebook.com, their code, they're about to push a new version of Facebook that everyone's going to use. Well, if you added some code, but it didn't work as intended, well, now when people try and access Facebook, it's now going to fail because of your code that didn't work well. So that's what code testing generally is for. I definitely recommend starting to look into it. But again, this is one that I feel like more is industry focused rather than kind of some research groups. The next thing is, okay, let's say that you've been working on your code. You did do code testing and you successfully tested it, but then your coworker goes to review your code and it doesn't work on their machine. And I think this is something most people will be able to relate to. Imagine that you've written a script on your machine, it works correctly, you try and give it to someone else and it doesn't work on their machine. This is a extremely common issue in industry and more generally, because you don't know what kind of operating system, packages, dependencies people will have on their machines. And the solution to this is called virtualization. Essentially, what virtualization does is it uses software that simulates hardware functionality to create a virtual system. So when I use virtualization software like Docker, what it's really doing is I put all of the stuff that I need to run my application into a Docker file, and then it essentially boots up a new version of an operating system on your machine, so that anytime anyone runs that Docker file, they get all of the files, all of the packages needed to run your application, and it can run on any hardware that you need at all. This is, again, if you think about for a research group, you don't really care about what your application is running on as long as it's working for you and the people in your group. But when you get into industry, you have no idea. There's various types of phones, various browsers, various operating systems, and so virtualization is a great way to be able to ensure that your code and your applications will run on a wide variety of devices. And then the one of the final things to touch on is the CI/CD pipelines. So let's say, we've kind of built this up. We have our project, we've done our testing, we have virtualization, but so we have this project that lives in a Git repository. All of our developers can make any changes they want, but how do we ensure that bad code doesn't get to the users of our application? So let's say we did code testing, but maybe whoever did the test didn't do enough testing, and they missed a couple things because we're all human, we all make mistakes. They were able to put it into Docker, they were able to virtualize it. It passed the test that we have, but then it gets all the way to the final part, and let's say that it hits this staging branch, and then we have someone who manually reviews it. So it passed all of our normal tests, but now we have someone to manually review it, and they spot the error so that it doesn't end up hitting production. So it doesn't end up going to facebook.com. It goes into something before that. Can you think of it as a a staging area, and they're able to catch that error before it actually goes live where our users could see it. So this one is a little bit more abstract, especially from the research side. But for industry, there's a strong desire to make sure that whenever anyone is writing code, pushing code into our project, that it is working correctly and that we don't end up pushing out something that completely breaks. So there's a lot of steps, and they're called CI/CD pipelines, which stands for continuous improvement, continuous delivery, to allow us to do that faster. And then the final piece that I want to talk about that is kind of outside of the pipeline, this is more just a general how a lot of data science is done, is cloud computing. So you can imagine, at Mississippi State, you have a variety of computers. Those computers are expensive, but let's say that tomorrow there were 30 new people who wanted to join the grad school program. There would not be enough computers. We would have to wait and go, wait until we could purchase 30 computers, and then let all of those people use them. And if you think about it, really, that's kind of what it is like when we have an application like facebook.com, right? Where it's, what if we have 100,000 people today who are accessing the website, and then the next day there are 200,000 people? How do we make sure that our application can scale? Because we don't want to have to continue buying hardware that will just sit there. We would rather have something that we can turn on and off as we need to. And that ultimately is what cloud computing does. Essentially, with cloud computing, there is a virtually infinite amount of possible compute resources that we can leverage, and we can just turn them on and off for our application as we need them, instead of having to actually buy the hardware to support our infrastructure. The reason I bring this up is most major companies, with a few exceptions, have moved their entire infrastructure to cloud computing. So it is very, very likely that if you do end up working in data science and industry, you will be working in a cloud environment. So understanding these is incredibly important. The platform, so AWS, Google Cloud, and Azure are the most common. There are differences between them, but if you understand one, then a lot of that knowledge will transfer between the three. So those were the things that I've kind of, I feel like I've picked up more post-PhD. But now I wanted to quickly touch on kind of job applications, interviews, and then kind of some recommendations. So for job applications, as a PhD, you're kind of in an interesting position because you're overqualified technically. You know the methods and materials very, very well. You're very strong in the mathematical background, in the methodology, but you're a bit underqualified on the business processes. So Git, SQL, pipelines, cloud computing, for example. So really, you should do everything that you can during your PhD to build up the second bullet as much as possible. The ways that you can do this: internships, personal projects. So you show them on GitHub. Have your GitHub username in your resume so people can go look and see what projects you've done. And also start looking early on at jobs you think would be interesting. You figure out what most of them require and start learning those right away. So things like, if you see you want to be a machine learning engineer, for example, and you see that of the machine learning opportunities that look interesting to you, all of them require you to know GitLab, for example. Then start learning GitLab now. So then, a year or 2 years when you start applying for jobs, you already have that on your resume as something you can talk about. The interview process wildly varies from company to company. So I'll give you some general trends, but this is definitely very much company specific. Generally, for larger companies, you're going to have more interviews, and they will likely all be individual interviews. So for example, when I interviewed for the Nike senior data scientist position, I had 7 interviews with various team members, the person who would have been my manager, the director, and a few others. Whereas for smaller companies, I've generally seen you have fewer interviews, as few as just one group interview with kind of all the team members and directors who would be making that hiring decision in the room at the same time. Be prepared. Most
interviews for data science positions will be asking you technical questions. I've gotten questions like, how would you do this in SQL? What are the 4 characteristics to know of ensuring that you have a good fit of a linear regression model? You're going to get technical questions, but there's a lot of great interview websites to freshen up on SQL, Python, Git, and so forth. So then once you are able to get a job, how does the data science team actually work? So the most common framework for working is called Agile. At every place that I've worked since graduating, this has been the key framework for working, and this is widely used across almost every tech company, though it kind of varies in specific implementation. But Agile was initially created for software development work. The idea is that we have a website, and we want to make incremental improvements to the website every sprint, which are generally 2 weeks. So we would think about something like, okay, I have facebook.com, and now I want to update the logo on develop, test, deploy, review, and launch stage all in 2 weeks. And then the next 2 weeks, I would figure out, okay, what's the next high priority thing that I need to do? This is something that it's going to sound a little bit kind of abstract, but this is something that actually, as going through your PhD, this is something you will actually naturally be very good at, because this is how R&D works in general, is you have to quickly test things, figure out if it works or not, and then either apply it if it works well or ignore it if it doesn't work well. I've left this slide in just as kind of a high level on what are some of the key terms in Agile. Because it is so familiar, I would definitely recommend anyone who's looking soon for a job to do a little bit of review on Agile, just to understand kind of what it is, what the main goals of it are. And here are just kind of some of the main terms for that. So with that, wanted to get to my recommendations. So I will say I've put these 6 down as like things I would strongly recommend you to have before you start looking for a data science job. But I will caveat that by saying that really I only had about 4 of these out of the 6 and was still able to get a job. So this is not something you have to know all of them or you will not be able to get a job. This is just something that if you do know all 6 of these things, along with having a PhD, I can guarantee you that you will have no difficulty finding a job whatsoever. So the 6 are: learn a programming language, Python or C++ is preferred, learn Git, know how to use it, learn SQL, create a GitHub repository with sample projects that employers can look through, become certified in one cloud computing platform, so either AWS, Google Cloud Platform, or Azure, and then start looking at jobs you think would be interesting and note common requirements. So for example, if you're looking at operations research requirements or operations research jobs, and all of them say, hey, you need to know Gurobi, start learning Gurobi. Because if you have expertise in what they're wanting, that makes you a more attractive candidate. The other things I have are nice to haves. These are kind of based on the job that you desire. So these are not going to be for all of them, but just ones that you may want to look into. So virtualization, CI/CD pipelines, UI development, so things like Flask, Django, JavaScript, or Shiny for R, deep learning experience, scalable computing, how do we do GPU acceleration, parallel computing, potentially domain expertise, and leadership experience. And I will say, with all of this, this is obviously kind of the nice to haves, and my recommendations are a bit, based on my experience. And so you may experience something completely different. Data science is a very wide field with a lot of opportunity in that. So take it with a grain of salt, but I do believe that, at least for the recommendations, those are ones that I would definitely push for if I could go back and do it again. I've added a few links here for places to learn or things to search for. These are for the recommendations specifically, and then these are more for the nice to haves. So I've included my GitHub. These are my code examples that I had when I was finishing up my PhD, and used them as a to show employers, hey, I know what I'm doing. So feel free to look through that. But I will strongly recommend just start small and continue adding school projects, add other projects that you find interesting. It does not have to be perfect or look great. It just needs to demonstrate that you know what you're doing. So with that, I know I ran a little bit over what I kind of intended, but I'll now open it up to any questions that anybody has.
Thank you.
Thank you, Jack. That was fantastic presentation. I have a question to start. Can you hear me?
Yes, I can hear you.
Did you have to take any like code test or machine learning test, like data science test for any of your applications?
So I have not, but I know it is very common to have to do that. Again, that's kind of where I was talking about. The interview process is very different for different companies. I have a few friends who've had like case studies where they'll be given, one was given here's a database of our past sales, apply some sort of machine learning model to it and write a report showing like what your findings were from that. So things like that are very common, but I personally have not come across anything like that.
Okay, yeah, we some of the previous PhD students have had to do had to take the test before they even got an interview, as they were asked.
Yeah, it's definitely common. It depends. Again, that's more on the larger the company that you're applying for, the more likely something like that will be to happen.
Okay. And then I have another question regarding so for your machine. So sometimes, like especially when I'm working on a project, my code won't be necessarily the cleanest. Do you what do you recommend? Have you had to run into this problem in industry, like with your coding experience, or like having to improve like your computational complex running of your code?
Yeah. So yes. So I think there's a couple of things there that I'll touch on. So first, kind of like the cleanliness of code. I would definitely recommend, especially for like putting a GitHub repository for employers together, I would definitely recommend like cleaning up the code, adding comments where possible. For the computational complexity part, yes, that is actually a very big issue, depending on the problem. But I'll give you an example of one thing that I had to do. Is we had a problem. We were doing natural language processing, and we were looking at n-grams, which are essentially n words in a row. You're looking at like phrases that are common together. And we had another data scientist who developed code, did that, and was able to get it to work successfully. But it ultimately took like 4 hours to run because there was a bunch of nested for loops. And so I actually spent like a full sprint using agile terminology to reduce that down to around 15 minutes. So it depends a little bit on problem specifically. But yes, there are a lot of times where you will be working on computational complexity because you do need to make your code faster while ensuring it's kind of the same quality.
What do you recommend for trying to like, is the software anything to or what do you recommend how to reduce complexity or learn how to reduce complexity? Do you have a
Yeah, so it's going to depend a bit on your specific language that you're using. The main things that I would do that are language independent would be looking at parallelization. So if you're able to run any sort of computations that are not dependent on one another, you can run those in parallel, and that will significantly speed up your code. The other thing is vectorization over for loops. So for example, Python is a good example of if I have a pandas column, if I want to add one to every row in that column, I could do something like for I in my column.shape, add one to each row and go one by one. Or I can do the vectorized option, which is just that column equals that column plus one. Anytime that you can use vectorization instead of for loops, you should definitely try to do that. And also for Python specifically, definitely try and use NumPy and pandas as much as possible when you're doing more of like the math heavy stuff, because it's all actually optimized in C, so it will be much faster than any Python that you can write. Again, it's going to depend on language, so that's just kind of a few things. But parallelization and then vectorization are usually the two things to like first look for with that.
Okay. So also in the comments, someone asked how how tough is it to get a data science job as an undergraduate? Like, is there a path for that?
So if you're an undergraduate, it is going to be pretty challenging to get a data scientist position. The reason for that being is generally for a data scientist position, you need to have a deep understanding of machine learning. You need to have a very deep mathematical background. It is possible. I do know a few people who have gotten it. Both were in the process of working on their master's in data analytics, and they were doing it as a part-time job alongside that. So it is possible. What I would recommend is looking for things that are close to a data scientist position. So a good opportunity that could lead to data scientists would be a data analyst or a business or a BI analyst position. I have multiple friends who are in positions like that, all of which kind of have the aspiration of going the next step to the data scientist position. So data analyst, BI analyst are both two like very good ones looking for undergrad. But I would, if you truly want to move into a full data scientist position where you're doing a lot of machine learning, I would strongly recommend at least trying to get your master's, or trying to see what internships you could get to give you kind of that experience as a data scientist before getting into a full-time position. It's unfortunately, there's a lot of people who want to do data science, and there are a lot of people who have PhDs in things like physics and other engineering fields that weren't able to get academic jobs, but end up fitting very well into data science. So it's just kind of a matter of kind of comparing your credentials against everyone else. But there definitely is a path for moving from an undergrad into a data scientist position. Hopefully that answered the question.
Does anyone else have any other questions for Jack? I think that answered their question.
Okay, cool.
Well, Jack, I don't think we have any other questions, but
okay.
I appreciate you coming and speaking to us, and you'll send me these slides, and I can share those slides with anyone that would like them.
Yep,
and
can do.
Go from there. And I've also recorded this presentation. We'll be posting it on our YouTube account.
Okay, cool. Awesome. Yeah, I'll make sure to send those slides your way.
Okay.
And then if anyone has any questions, I'll put my email in the chat. And feel free to email me. I know some people enjoy asking questions directly rather than kind of in a big space like this. So feel free to email if you have any questions later on about data science. I'll be happy to answer.
Hey, Jack. Just want to say thank you. Really enjoyed your presentation.
Oh, awesome. It's great to see you, Dr. Murphy.
Yeah, I think you talked about some of the aspects that, typically the graduate students, they don't usually see that kind of, tones or that kind of specific terminology. So for instance, you stressed a lot about, let's say, Git. You talked about the coding testing. You talked about the virtualization. I mean, those things, again, you already mentioned that. Those are some items that in academia you really don't have to care about. But
Right.
for industry, they are super important. So I'm glad that you're actually very much on track, and you mentioned all the some really nice skills that everyone should have. If you can also talk a little bit more about specifically the cloud. So is there any you talked about the certification. Is there any place you know that where we could have that certification, or any kind of specific guidelines, or any kind of cloud related certification?
Yeah, so if you can see my screen, sorry, with the web app, it's being a bit weird. I would definitely recommend trying to do one of these three. So with all of them, the way that they work is, so I have the AWS one, and I have another AWS one as well. But the way that it works is they have a lot of material online. There are also Udemy courses that have a lot of material on them. And then AWS offers the class. You can take it through any testing center. So you should be able to take it through a testing center at Mississippi State, and you get your results right away. And that's one thing I think that, and this is where I think cloud computing is definitely something that could be leveraged a lot within the research groups if you take the time to really understand it. Because the big benefit that you have is we don't have to rely on what hardware we physically have, right? So if you just need, for one project, you need something that can have 100 gigabytes of RAM, for example. Well, you can spin that up in the cloud. You pay per hour instead of paying for the full hardware. And there's a lot of benefits that you can get from that, even in a research setting. By not having to purchase something, a hardware, machine that lives at Mississippi State that's 128 gigs of RAM, you can just spin that up in the cloud, for example. So I would definitely recommend, the slides I sent to Christian, there's 3 at the very end. I've gone through AWS just because that's what my previous company was using. I found it fairly straightforward. It's fairly easy to learn, but again, it translates between AWS, Google Cloud Platform, and Microsoft Azure. So it just depends on which one you're most comfortable with. But it's definitely something that I could see being very beneficial for the research groups. But there's definitely a bit of a learning curve there on that. So yeah, hopefully that answers your question.
Well, that's perfect. I think there are already several materials. I think the students who are interested on the data science track, the advice that actually Jack provided. I think, Jack, the best thing I liked about you that you made 2 slides, one on like, okay, what you must have to have, which is actually perfect. And also the second part that you mentioned that, okay, well, those are something like after you have that, like the most basic elements, then, this is the next step that you need to have. So I think that list is actually, I think all the students should have that list in front of their desk, and then they should start, okay, well, those the items that you listed as must have, like are they really comfortable on that level? And in general, actually, the data science job, there's a lot of competition nowadays because everyone claims to be a data scientist. Everyone is doing some type of data science type of job. Not only for CS, IE, ME, EC, everyone is doing some type of data science job, even outside the engineering domain. So to place yourself to a data science job, everyone need to show also some type of capabilities that Jack also highlighted. Specifically, he talked about demonstrating them into some type of a GitHub account where you can show what kind of work you have been doing. So those all are actually important. And I think one other point that I really liked your presentation that you said the communication part, which is again extremely important in academia.
Yeah.
Sometimes we just overlook, but I think the best part I liked your presentation is that you talked about some of the really important elements that actually someone should have for once they actually start working on industry. And I can tell you, if someone from academia, if you prepare that presentation, it would not be as targeted as you did. So great job, Jack. Really enjoyed it.
Well, thanks. Yeah. I'm glad that that's how it came across, because that's what I really wanted to push is, there's not academia is, missing something. It's just, these are 2 different problem sets that you're trying to solve, and there's different tools for that. So I will say, out of the must-haves, I think I graduated with like 4 out of the 6. So you may not need all of them, but I would say it definitely is a good goal to go towards, is to try and get as much as you can to make yourself, like you're saying, as competitive as possible, because it is a competitive field trying to get into a data science position. But the good thing is once you're in and you've done good work, from there it becomes a lot easier to start moving around to other jobs and other positions. But getting the first one definitely is the most challenging part for a lot of it. So
good, very good, Jack. Thank you for your time.
Yeah, absolutely, happy to do it. Glad y'all invited me to do it.
Right. Well, thank you, Jack. And yeah, again, I'll have the slides for everybody. And yeah, again, thank you for your time.
Yeah, absolutely. Thanks for inviting me. Hope y'all have a good rest of your day.
You too.
Yeah.
Thanks. Bye.
Bye. Bye.
Thank you, Jack.